Last few lectures we have been solving the oscillatory flow in a pipe, unsteady fully developed flow in which the pressure has a sinusoidal dependence, in which the pressure has a sinusoidal dependence on time. Okay. And the way we had solved that was to write down cos omega t as the real part of e power I t star, where t star is the scale time, t star is equal to omega times t. Okay. Because we know that for a given sinusoidal forcing, the response has to have the same frequency as the forcing, we wrote down the response, the velocity response as a function of r times e power I t, substituted that into the equation and got a solution for the spatial dependence of the velocity profile. Okay. So, if you recall that the spatial dependence of the velocity profile was of the form of a Bessel function, okay, was in the form of a Bessel function. Okay. Was in the form of a Bessel function, and I had to multiply it by e power I t and take the real part of that solution in order to get the actual velocity profile. Okay. So, this is a complicated function for which you have to get the solutions numerically. You have a complex function multiplied by e power I t and then take the real part, and I had sketched out the numerical solutions for you at different phases in the pressure oscillation. Okay. I had sketched out the profiles for you. At low Reynolds number, the profile is nearly parabolic and the pressure gradient is a maximum positive, the velocity has a negative, okay, minimum parabolic, and then it is 0 when the pressure gradient is 0, has a positive maximum when the pressure gradient is at its minimum, okay, negative value. It is similar to the velocity profile you would have got had you taken the instantaneous value of the pressure gradient for a steady, okay, profile, okay, in the limit of low Reynolds number. And that I had explained to you is because for low Reynolds number, the diffusion time is much smaller than the time period of oscillation. So, momentum diffuses instantaneously across the entire channel, the entire pipe over a time period small compared to the time scale for the change of the pressure. Therefore, you get the same profile you would have got for a steady flow with the instantaneous value of the pressure, and we had seen that. Okay. We had seen that in the limit of low Reynolds number, this is the solution for the velocity profile and this is the solution for the scaled velocity profile. This solution is strictly applicable only when the Reynolds number is identically 0. If the Reynolds number is small but non-zero, we can use what is called a regular perturbation analysis, where the velocity is expanded in a series in this small parameter, substituted into the equation, and a sequence of equations are obtained for each, okay, power of Re omega. Okay. By collecting all terms in the original equation that have that same power of Re omega, okay, you get a sequence of equations. And you have a sequence of boundary conditions as well by expanding the boundary conditions also, okay, in the parameter Re omega. Okay, you also expand the boundary conditions in the parameter Re omega, and then you can solve it sequentially for Re omega power 0, Re omega power 1, Re power omega power 2, and so on. The equation for Re omega power n contains as an inhomogeneous term the solution for Re omega power n minus 1. Therefore, you can solve each one explicitly. Okay. And I had shown these solutions for you, and I had said that these asymptotic solutions, regular perturbation solutions, are in good agreement with the numerical solutions even for Re omega equals 1. Once R omega becomes about 10, then these asymptotic solutions are no longer in agreement with the numerical solutions. Okay. Obviously, because the Reynolds number is becoming large. Regular perturbation expansion, because the equation had a small parameter in it. Okay. In the limit as that small parameter goes to 0, the solution of the equation, okay, if you take the solution and then substitute R omega equals 0 in that solution, what you get is identical to what you would have got had you solved the equation with R omega equals 0. Okay, so that is a regular perturbation. Then we consider the case where R omega is much larger than 1. We had to rescale our velocity differently by the inertial scales. Okay, we had to rescale our velocity by the inertial scales, and in the equation we get this parameter 1 over R omega multiplying the viscous term. Okay, you get the parameter 1 over R omega multiplying the viscous term. Okay. So, you express the velocity as the real part of a spatially dependent part times e power I t, substitute it into the equation and you get an equation for V tilde. Okay. And boundary conditions are of course 0 velocity at the wall and the velocity gradient is 0 at the center. Okay, the derivative is 0 at the center, the usual boundary conditions. If we neglect this term altogether, okay, if we neglect this term, the viscous term altogether in the differential equation and try to solve it, okay, we get a constant value of V. Okay, we get a constant value of V. Okay. With this, we can satisfy the boundary condition at the center, but we cannot satisfy the boundary condition at the wall. Okay. The reason we cannot satisfy the boundary condition was because the original equation was a second order differential equation, a second order ordinary differential equation, and if you integrated that second order equation, there would be two constants, and with those two constants you could satisfy the boundary condition. When we neglected the highest derivative, then the resulting equation was only an algebraic equation. It was not a differential equation, and therefore, the solution does not contain constants, and therefore, you cannot satisfy the boundary condition. That is the mathematical reason that we are not able to obtain a solution for this equation. When a small parameter multiplies the highest derivative and you neglect that, the approximate equation does not contain the highest derivative, and therefore, you cannot satisfy all of the constants that were originally present in the original equation. Okay. That is the mathematical reason. The physical reason is as follows. Viscous stresses are the mechanism for momentum transfer to the wall. Okay. The flow is along the x direction. There is no velocity perpendicular to the wall, and therefore, there is no convective transport perpendicular to the wall. Therefore, the momentum transport to the wall, which will result in the velocity coming to 0 at the wall, that momentum transport has to necessarily take place due to diffusion. When we neglect diffusion, there was no momentum transport to the wall, and therefore, the velocity cannot come down to 0 at the wall. There is no retardation effect due to the stress exerted by the wall, and because of that, the velocity cannot come to 0 at the wall, and therefore, you cannot satisfy the velocity boundary condition. Okay. This is however unphysical, okay, because if you consider the flow close to the wall, okay, there is a balance between momentum diffusion from the wall, okay, and the velocity that goes in the positive and negative direction, which convects the momentum along the wall. Okay. Even if the Reynolds number is large, okay, even if the Reynolds number is large, okay, there will be momentum diffusion, but that will be restricted to a thin region close to the wall. Okay. There will be momentum diffusion, but that will be restricted to a thin region close to the wall. Okay. How thick is the region where there is momentum diffusion? Okay. The time required for momentum diffusion, okay, over a distance. Okay. So if we take the time period of oscillation, okay, okay, t, which was equal to 2 pi by omega. Okay. Within this time period, how much does momentum diffuse? Okay. How much does momentum diffuse from the wall? Okay. Obviously, it diffuses to a distance that is small compared to the radius, okay, in the limit of high Reynolds number. The distance, the diffusion, okay, the distance to which it diffuses just from dimensional analysis has to be equal to nu by t, okay, whole power half. Okay. The distance to which it diffuses cannot depend upon r because it is much smaller than the radius of the pipe. Okay. So, the distance to which it diffuses will be proportional to nu by t whole power half, okay, which is the same, okay, to within a constant factor as nu times omega whole power half. Okay. And the distance to which it diffuses, okay, I will call this as delta. Okay. Delta by r, okay, the ratio of the diffusion distance and the radius of the pipe is equal to nu omega by r square. I am sorry, I made a mistake here. This should be nu times t. Okay. Kinematic viscosity has dimensions of length square per time. Okay. Kinematic viscosity has dimensions of length square per time. Kinematic viscosity times time has dimensions of length square. Okay. So, that is the distance. Okay. So, this is equivalent to nu by omega to the half to within a factor of 2 pi. So, therefore, this is equal to nu by omega r square per half. Okay. This is equal to r e omega per minus half. Okay. So, the physical picture is that even though the Reynolds number is large, okay, there is still diffusion from the surface over a distance comparable to r e omega power minus half times the radius, okay, thin region very close to the wall. The thickness of this region goes to 0 as r e omega goes to infinity, proportional to r e omega power half. Okay. But in this region, within this region, momentum diffusion is going to be comparable to convection, and therefore, the diffusion term has to be included within the conservation equation in this region, okay, very close to the wall. Okay. So, how do we include this term? Okay. So, the way it is done is to, okay, define a scaled coordinate. Okay. So, we know that if we focus our attention very close to the wall, okay, this is r is equal to r, okay, and I can take the distance from the wall as, okay, okay, a scale distance, okay, as w, okay, w is equal to r minus r, okay, by r, okay, into 1 over what is called a boundary layer thickness. Okay. So, basically this thin region close to the wall, I am dividing it by a small number here. Okay. I am dividing it by a small number here in order to expand this out, so that within this region diffusion and convection are comparable. The pressure gradient, the time derivative and diffusion are comparable. Okay. So, this is what I will call my scaled distance from the wall. Okay. Okay. and I will choose the value of delta in such a way that even in the limit of high Reynolds number within this region, diffusion and convection are comparable. Okay. So, this is the scaled coordinate from the region. Basically what I am doing is that thin region close to the wall, I am expanding it out by dividing by a small number delta star. Okay. And that small number delta star I will relate shortly to the Reynolds number in order to get a balance between the acceleration term and diffusion in the original equation. Okay. Recall that my original equation was I v tilde is equal to minus 1 plus 1 by r d by dr of modulus. And from this I can write r star is equal to 1 minus w times delta. Okay, so r star is close to 1 in this case. Okay. And d by dr, okay, these should be total derivatives actually, because v is only a function of r. Okay. Just expressing r in terms of this parameter w, which is a scaled distance from the surface, scaled by this parameter delta star, okay, which we will relate shortly to the Reynolds number. Okay. So, substitute into the equation I v tilde is equal to minus 1 plus 1 by r e omega delta, as I said, is a small number. Okay. So, yeah. Delta, as I said, is a small number, and therefore, I can neglect delta w in comparison to 1. Delta is a small number, w is order 1, okay. W is an order 1 quantity. Delta goes to 0 as the Reynolds number goes to infinity, while w continues to remain finite as the Reynolds number goes to infinity. Okay. So, this simplified equation is and the ratio of diffusion and the acceleration term and the pressure gradient will continue to remain of order 1 in the limit of high Reynolds number if this term is of order 1 in the limit of high Reynolds number. Okay. Okay. So, if this r e omega times delta square is of order 1 or delta is proportional to r e omega power minus half. Okay. Diffusion and convection will be continue to be of order 1 within this region of thickness delta close to the wall. Okay. And this, okay, this delta star is basically delta by r, which as we had anticipated on the basis of physical arguments that it has to scale as r e power minus half. Okay. So, this Re power omega times delta square has to be some constant. Okay. It does not matter what the value of the constant is. Okay. It turns out that the solution in terms of W will depend upon the value of the constant. The solution in terms of the original variable R star will not be a function of that constant. Okay. So, we can set that constant equal to any value. Okay. So, I will just assume an unknown constant here, Re omega times delta star square is equal to some constant C. Okay. And I substitute that into the equation. Okay. I will call it as C square. Okay. That is easier. Okay. C square. Okay. I will get I V tilde is equal to minus 1 plus 1 over C square d square V by dW square. Now, this is a second order differential equation that is easy to solve, inhomogeneous. So, there is a homogeneous solution which is just a constant V is equal to I. Okay. This satisfies the equation, the general equation, plus this is the particular solution that satisfies the one solution of the inhomogeneous equation, plus you have homogeneous parts C1 e power square root of I C W, okay, plus C2 e power minus square root of I C W. Okay. Okay, the homogeneous equation in this case, okay, is basically d square V by dW square is equal to C square I V, okay, without the inhomogeneous term. Okay. So, the solutions are exponentials, okay, with square root of I in the exponent. Okay. So, you know that e power I t is cos t plus I sin t. So, you have to express this in terms of the real and imaginary parts and then take the values. Okay. Boundary conditions. Okay. At R star is equal to 0, partial V or dV by dr star is equal to 0. Okay. Note that R star is equal to 1 minus delta star W. Okay. So, R star is equal to 0 implies that W is equal to 1 by delta star. Okay. Delta star is a small number, Re omega power minus half I had told you. That means that W goes to infinity. Okay. As W goes to infinity, the slope has to go to 0. Okay. As W goes to infinity, the slope has to go to 0. Okay. In this equation, this first term goes to infinity as W goes to infinity. Okay. As W goes to infinity, this first term goes to infinity. Okay. Therefore, the constant C1 has to be equal to 0. Okay. And as W goes to infinity, this second term, okay, is exponent of a negative number, this the exponent of a negative number, this goes to 0. Okay. So, the condition that as you go away from this viscous layer close to the wall where viscosity is important, as you go away from that towards the center, the velocity profile has to be finite. Okay, the slope has to go to 0. That fixes the value of this coefficient, okay, C1. The second coefficient C2 is determined from the condition that at R star is equal to 1, V is equal to 0. Okay. R star is equal to 1 implies that W equals 0, okay, because W is equal to 0 at the surface. Okay. As I told you, W is a coordinate, that is the distance from the surface. At the surface, W is equal to 0. With that, I will get the velocity as I into 1 minus e power minus root I C W. and I can express this back in terms of the original variables I into 1 minus e power minus root I c into w, if you recall, was 1 minus r star, okay, by delta star c. I am sorry, by delta star. Okay. Recall that w was equal to 1 minus r star by delta star. I substitute that in there, and also I had that delta square times r e omega is equal to c square. That means that delta star is equal to c by r e omega per half. Okay. So, this is equal to I into 1 minus e power minus root I c 1 minus r star divided by r e omega power minus half into c. Okay. And you can see that these constants cancel out. Okay. These constants cancel out. I told you that you can assume any value of the constant. The solution in terms of w here will depend upon the value of the constant. The solution in terms of the original variable r star here will not depend upon the value of the constant. Okay. So, my final solution is V tilde is equal to I into 1 minus, I will write this as an exponential, okay, just to make it clearer, minus root I into 1 minus r star into r e omega power half. Okay. Okay. Times r star, I am sorry, 1 minus r star. Now, I can substitute for square root of I. So, now I have to find out the actual velocity is equal to the real part of V tilde e power I t. That is the original velocity. Okay. And in this expression here, okay, I have to use the substitution, okay, that square root of I, the identity, is equal to 1 by root 2 plus I by root 2. Okay. That identity has to be used along with the identity that e power I t I times any function x is equal to cos of x plus I sin of x. Okay. So, using these two, we can get an analytical solution for this V star. Okay. We can get an analytical solution for V star. It has a slightly complicated form, so I will not go through the details of the form. Okay. All I will say is that by this solution procedure, the final solution that we get, okay, it turns out that it is actually in quantitative agreement, okay, with the solution that you get in this case, okay, at r equals 100. Okay. There is quantitative agreement between the solutions that you get, okay, using this procedure. Okay. Okay. So, this approximation quantitatively captures the velocity profiles in the limit of high Reynolds number at r e omega equals 100. Physical picture is that since the momentum diffusion, time for momentum diffusion is long compared to the time period of the oscillation, therefore, momentum diffuses only to within a thin region close to the surface. As we had seen this numerical result. It diffuses only to a thin region close to the surface. Everywhere else there is no momentum diffusion. Therefore, the velocity is a constant everywhere else. You have a thin region close to the surface where the velocity is the effect of the retardation due to the stress exerted by the wall is experienced in the velocity profile. The thickness of this region decreases proportional to r e omega power minus half in the limit as r e omega goes to 0. The thickness decreases and however, the velocity does decrease to 0 within this region because of the momentum diffusion from the wall. Okay. And this procedure is called a singular perturbation expansion. Okay. It is called a singular perturbation expansion. It is called a singular perturbation expansion. The reason is because the original equation had a small parameter. Okay. The original equation had a small parameter. Okay. The small parameter was 1 over r e omega. Okay. The solution that you get by solving the complete equation in the limit as the small parameter goes to 0, which is a constant, is not the same as the solution you get by setting that small parameter equal to 0 in the final solution. Even in the limit as r e omega goes to 0, there is momentum diffusion up to a certain thickness and the velocity has to decrease to 0 at the wall. Whereas if you neglected viscous effects in the original equation, you find that the velocity is just a constant and you cannot satisfy the boundary conditions. Therefore, the solution of the complete equation in the limit as r e omega goes to 0 is not the solution of the simplified equation where you neglect the term that multiplies the small parameter. And for that reason, these kinds of solutions are called singular perturbation solutions. And it is necessary to postulate a thin boundary layer close to the surface where the velocity decreases to 0 in order to obtain the accurate solution of this velocity profile. So, this completes our analysis of oscillatory flows. I considered for you two cases. The original equation, in this case we could solve it and get a numerical solution. In many cases you may not be able to get a closed form solution. However, you can take limiting cases r e omega small and r e omega large, use a regular perturbation expansion in one limit to get the solutions for small values of the Reynolds number. In the limit of high Reynolds number, if you neglect diffusion altogether, you cannot satisfy boundary conditions because the 0 velocity condition at the wall is due to the momentum diffusion. And if you neglect momentum diffusion, you cannot satisfy the boundary condition. It is necessary to postulate a thin region close to the wall whose thickness decreases as the Reynolds number increases in such a way that diffusion and in this case the unsteady term are comparable in this region. And you can use that in order to find out approximate solutions. So, this completes our discussion of oscillatory flows, and I will continue in the next lecture with the next topic on conservation equations. I will see you then.